Let's continue a lecture on metals and what type of steels are there. Steel can contain up to 2% carbon. We already know that. And varying the amount of carbon gives steel different properties. For example, a higher carbon content makes a hard steel. An alloys of iron and carbon, it consists up to 1% carbon in iron. Such steels are often referred to as plain carbon steels, which can be subdivided into three categories. Plain carbon steels, low carbon steels, medium carbon steels. And different types of steel are classified by how much carbon they contain. So, low carbon steels contains less than 0.25% carbon. Of all the different types of steel, those produced in the highest quantity are low carbon steels. Typically, these contain anything, and we know that 0.25% carbon, and chemically they are composed of ferrite and perlite. Low carbon steels are relatively soft and weak in comparison to other types of steel, but have excellent ductility. In construction, they are used as structural I-beams, as sheet forms in buildings, bridges and pipelines. They have a yield strength of about 280 megapascal, tensile strength of around 550 megapascal, and a ductility of 25% elongation. At failure, they strength up to quarter of their original length. That 100 millimeter sample will strength to 125 millimeter at failure. Another groups of low carbon steels as high strength low alloy steels. In addition to carbon, other alloying elements include vanadium, nickel, copper, and molybdenum. The combined alloyed content is up to 10%. As a result, they have higher strengths than plain low carbon steels of around 500 megapascals, without compromising of ductility and machinability. These steels have applications in construction, civil engineering, where structural strength is of great importance in bridges, support columns, in multi-story buildings and towers, etc. The next type of steel is high carbon steels. High carbon steels usually contain of more than 0.5%, half of percent, and usually from 0.6 to 1.4 carbon. These alloys are the strongest and hardest of the plain carbon steels. However, the disadvantages is that they have the lowest ductility. As ductility and toughness are such important properties required for structural steels, hard carbon steels have limited application or usage in construction. They are mainly used as cutting tools, as well as high-strength wire. Hard carbon steels can have yield strength up to 1,700 megapascal, tensile strength up to 1,800 megapascals, and ductilities as low as 5%. The next type of steel is medium carbon steels and contains more than 0.25% and up to 0.6% carbon. These alloys have higher strength than low carbon steels, but lower ductility and toughness contains more than 0.5% carbon. However, they have a good compromise and balance between strength and ductility. The main application in civil engineering is in high-strength structural components, where a combination of high strength, ductility, and toughness are critical. Medium carbon steels are also extensively used in the railway industry. They have a yield strength of about 450 megapascal, tensile strength of around 600 800 megapascal, and a ductility of about 15–20%. Elongation at failure, they strength up to 1/5 of the original length. That is 100 millimeter sample will stretch to 115–120 millimeter at failure. Most constructional steels contain between 0.15 and 0.4% of carbon. Thus, depending on application and strength requirements, mainly medium or low carbon steels are used in construction structural steels. Two other important types of steel are stainless steel, an alloy of iron that contains at least 11% chromium and smaller amount of nickel and carbon. And other type, titanium steel, an alloy of iron and titanium. Next, the cast iron is also an alloy of iron and carbon, consisting of between 2.1 and 4% carbon in iron. Therefore, cast iron contains up to 10 times more carbon than steel. This carbon gives it excellent casting properties, making it possible to produce many complex items and shapes by casting. This is explained by referring to the FAS diagram that I will show later. Now we can see that as the carbon content increases, especially from 2 to 4.4%, the melting temperature reduces. Refer to the liquid phase at the top of the figure. Thus, they are easily melted and more amenable to casting. In general, cast irons tend to be brittle with the exception of malleable cast iron. They have a tensile strength of 150 400 megapascal. Cast iron has limited application in construction. That's very important, and we cannot use it. The next frost iron, essentially pure iron. Frost implies the alloy is relatively ductile. It used to be made and used in very large quantities for construction and general engineering purposes in Victorian times, 1800s and earlier. That is bridges, metal fences, etc. But today it's not produced anymore, except for tiny amounts made for demonstration purposes in industrial museums. And of course, galvanized steel, as we shall see already, iron hand steels is highly prone to both weight and atmospheric attack by oxygen. Corrosion, therefore, it's vital to protect steel in any application. One method is by coating the material with a protective or corrosion-resistant layer. As zinc has excellent resistance to corrosion, is chemically compatible with steel and very cheap. It's the ideal material. The zinc is applied to the steel metal by a process known as galvanizing. Galvanized steel has gone through chemical processes to keep it from corroding. The steel gets coated in layers of zinc because rust will not attack this protective metal. During the galvanizing process, the steel is submerged in melted zinc. The chemical reaction permanently bonds the zinc to the steel. But the zinc exactly a seal like paint, because it doesn't just coat the steel, it actually permanently becomes a part of it. A chemical reaction takes place between the zinc and iron molecules, thus forming a homogenized material. The most external layer is old zinc, but successive layers are a mixture of zinc and iron, with an interior of pure steel. These multiple layers are responsible for the amazing property of the metal to withstand corrosion, inducing circumstances such as moisture, air, or salt water. The zinc also protects the steel by acting as a sacrificial layer if for some reason rust does take hold on the surface of galvanized steel, the zinc will be corroded first. This allows the zinc to prevent rust from reaching the steel. The major advantage of this process is cost. Thus, given the large scale of steel structures required in construction, the vast majority of steel used in construction is galvanized. Stainless steel. Stainless steel is an alloy of iron, carbon, chromium, and nickel. Stainless steel was discovered by accident in 1913 in Sheffield, and the most common form contains 18% chromium and 8% nickel, and it's usually referred to as 18 divided by 8 stainless steel. Chromium is very expensive, and so stainless steel is also expensive, around 10 times the price of ordinary plain carbon steel. The material is highly resistant to corrosion, rusting, in a variety of environments, especially the ambient atmosphere. Chromium is the predominant alloying element, and concentration of at least 11% is required. In addition, nickel and molybdenum also enhances the corrosion resistance. As chromium has such a strong affinity for oxygen, it rapidly reacts with oxygen to form a protective passive layer, chromium oxide. As a result, the stainless steel has excellent resistance to corrosion. Indeed, it provides superior protection to galvanized steel, but due to cost, it would be too expensive to consider using stainless steel for structural application in civil engineering. As a result, stainless steel are utilized as cautery, gas turbines, boilers, nuclear power stations, etc. Properties of steel. We already know some properties, and why is steel such a popular material? The reason is that it has a remarkable combination of properties, and it also has the merit of being inexpensive. It's cheaper than any other metal except cast iron, with steel prices beginning at about £700 per ton. In terms of its mechanical properties, it has high stiffness, high Young modulus. This means that a steel structure placed under load will not distort or deflect elastically very much. High strength, high tensile strength. This means that the steel will not break under high loads. Metal possesses tensile strength unlike stone, concrete, brick, and other. A large suspension bridge such as Humber Bridge or a cable stay bridge like the Dartford Bridge over the Thames would be impossible to build without steel. And also, very important properties is good ductility. This is capable of undergoing considerable plastic deformation before it breaks. Its ductility means that it's capable of being shaped by rolling, folding, drawing, etc. into any desired shapes. Angle, channels, I-beams, and other shapes. Steel also has quite a high fracture toughness. A table with mechanical properties of the common plain carbon steels summarizes the main mechanical properties of the common plain carbon steels. Although steels have in general highly desirable mechanical properties. They also have some properties that are not so good, including the following: corrosion, high density, poor fire performance. We understand that steel is prone to wet corrosion. The reason is that it's a two-phase material. That is, its microstructure consists of two phases, ferrite and perlite. You know that ferrite is virtually pure iron and perlite a mixture of pure iron and iron carbide. Ferrous iron, being virtually pure iron, is single phase and so is much more corrosion resistant than steel. And of course, high density. You understand that steel has quite a high density. And 7,800 kilograms per meter in 3 cubic meter. So structures and components made from steel can be rather heavy. This is not usually a problem with buildings, but occasionally weight is important, and this can rule out the use of steel. And of course, poor fire performance. As steel is so dense and is such a good conductor of heat, it doesn't perform well in fire unless it's protected. Steel loses much of its strength of heated to 1000 degrees temperature. Most building fire don't reach temperature higher than 700-800 degrees, but if part of a steel structure is heated to this temperature, the steel will buckle or collapse under the load it's carrying. And steel also expands when heated, and expansion stresses are also responsible for some of the problems that occur with unprotected steel works in fires.